All right. So it's
Great
car day
dum-dums
today.
make me want to
Yahoo for car day. Okay. So based off of my first two classes, I was subbing for Mrs. Hill this morning. So based off of those two, we're tweaking the schedule just a little bit. So I haven't had a chance to go in the back yet to tweak it. However, you will still have some videos to watch tomorrow, or not tomorrow, but they will be posted this afternoon, and you'll have to watch them before next week. Okay? So we'll have some videos for that, and then some notes to go along with that. You'll get the note sheet for that tomorrow. You'll also get a note sheet for tomorrow's class tomorrow. All good stuff. Okay? Still looking at next week, Wednesday, being a formative, and then still looking at testing on the 20th, okay? Because then it's trick time. All right. So, what was your first car? Now, for Mrs. Hill, her first car, you'll learn in a little bit, was a Ford Pinto. The thing about the Ford Pinto, and it says, keep off my rear, I'm explosive, because Ford Pintos had a design flaw. The design flaw was the gas tank was located right in front of the rear bumper. So if the Ford Pinto got hit from behind, it exploded into a fireball because it punctured the gas and then exploded the car. Okay? So Mrs. Hill was driving a loaded around when she first started driving. Mr. Roth had a Ford Escort. I don't necessarily know if it was 4-door or not, but he had something that looked similar to that. Me, I started out in a 1980 forest green Volkswagen Rabbit, and it was a phenomenal car, even though it only had one working speaker, no air conditioning, no power windows. It had four on the floor. 4 on the floor, and it was diesel. And then, and then I let Mom drive it.
Oh no.
And what did Nancy do? Busted the head gasket on it.
Oh, Nancy.
And there wasn't enough money left in it to fix it, so my parents said, gone. I had it for like a month.
Wait, did she drive it once?
Once. Well, it was a hand-me-down car. It was the old family car.
Well, yeah, but then it was yours. She drove it once.
Yeah, exactly. Yeah. Thanks, Mom. Yeah, exactly. So then I got a white. Mine was 2 doors, none of this 4-door, sedan stuff. Mine was a white Jetta, gas, so it was quieter, which was nice. Air conditioning, bougie bouge, okay. 5-speed instead of 4-speed. Oh yeah, but it had also one little problem. As I was driving down the road, the steering wheel would lock up, like literally lock up, and I'd have to jerk the steering wheel to get it unlocked. Yeah. Safety first, kids. Safety first. Okay. All right. So we're gonna get to that stuff in a minute here. What example number 3 is a phenomenal type example. Okay. So let's talk about exponential modeling here first. Okay. So if you are following along and like to label your notes and all that fun stuff, this is section 3.2. Okay. And it's all about exponential modeling and logistic modeling, which we'll get to now next week. All right. So let's model this scenario. Okay. Let's say you are a nice child and you go and you decide to rake your yard with leaves. It's fall. It's turning into beautiful fall colors, as one of the reasons why I love teaching in this room, because we get a beautiful fall landscape. Okay? So you rake your yard. You spend hours and hours and hours raking your yard. Okay? And you do a great job. Go. Or what? You spend hours and hours and hours raking your yard. And then you say, well, I got to put my rake away in the garage. So you go into the garage, you put your rake away. Mine gets hung on the wall. Some people, it just goes in like in a corner. And I get it. Everybody's different. And you turn around and you look out at your freshly raked yard and there's 50 leaves. It's like they don't have a soul. And they just keep coming.
So it's like they don't have a soul.
They're just mean. Okay?
No.
So we're going to call that, and I'm going to refer to that as the moment. Okay? We're going to call that moment time 0. That's when your whole world restarts. Okay? So we're going to call that time 0. Okay? So at 0 hours, there are 50 leaves on the ground. And then you sit there and you start watching them for an hour. Okay? So you're watching and you're just like mumbling underneath your breath and you're like, stomping the ground and you're throwing a little mini, hissy fit, temper tantrum, whichever one you prefer. Okay? And you say, they're increasing. The number of leaves are increasing by 8% every hour. Okay? So my question to you then is, after 1 hour, how many leaves are on the ground? Figure it out. I'll give you a couple minutes. Did you want 54 leaves on the ground? Do we all agree with that? Okay, now mathematically speaking, I agree with 54 leaves on the ground, but I would like to know how you calculated that there are 54 leaves on the ground. Okay, you did it by 1.08 because it was increasing. Okay, so you went by 1.08. Did anybody do it differently? Anybody do it, they multiplied 50 by 0.08 and then had to add 50? Okay, right? That's fine, that works. Okay, right? So we can always do it. You can always multiply by whatever percentage that the rate is and then add it if it's increasing to your last value. Subtract it if it's decreasing. Okay? But the multiplying by 1.08 makes it go a lot faster and a lot cleaner. And you'll see that as we go into the rest of our day. Okay? So this was 50 times 1.08. Okay? So now you've sat there and you've calculated this stuff and you're like, oh, I gotta take a break. One of those, oh, I gotta sit down. So you go into the house and you watch 2 episodes of The Office on Comedy Central. Okay? Because The Office is your go-to show that you can just throw on and pick up on it wherever you can. Okay? If not, should be. It's really good. It's really funny. The more times you watch it, pick up on more stuff. Very good. So now it's 2 hours after moment. How many leaves are now on the ground? Okay. How many leaves we got on the ground now? A little over 58. 58.32? Yeah. Now, logic question for you. Can I have 0.32 of a leaf? Yeah? A damaged leaf? A leaf that got cut in half on its way down? Or cut third? If this were a people problem, can I have 0.32 of a person? No, that one I can't. Okay, because we're not picking up. Has anybody been watching Dahmer on the flicks of net?
Yes.
I heard it's like creepy,
It's like so
disturbing.
sad.
Yes, haven't watched it yet. No spoilers. Okay, that might be my weekend binge. Okay, all right. So this is 50 times 1.08, because that was my 54, right? But then I multiplied that by another 1.08. Okay? So now we're coming. I promise. She's coming. She's leaving right here. So now you spent an hour doing that. You've spent an hour watching The Office. Now you're hungry. Okay? So now you're going to spend an hour eating. Okay? So now 3 hours later, how many leaves are on the ground? Again, let's round to 2 decimal places. 3 hours after, how many leaves on said ground? Anyone? 62.99. And so that was 50 times 1.08 times 1.08 times 1.08. Now, can we make a exponential model based off of that? Yes? Okay. What would my exponential model? I'm going to go leaves of t. Yes, ma'am.
50 times 1.08 to the x.
But I would go t power, right?
Oh, yeah, you're
If you went L of x, then we would go X. Okay? Agree with me on that? So now, after you ate dinner, you say to yourself, self, I'm not going back out today. I'm done. I'm done with these leaf things. They just keep coming and coming and coming. Okay? So you say to yourself, I'm going to go out tomorrow. And I'm going to start at the same time tomorrow as my moment. Okay? So how many hours would that be? 24, right? Okay, 24 hours. So how many leaves are in the ground, or on the ground, not in the ground, on the ground 24 hours later? 1 day later. Anyone?
317.
317.06 leaves. Because we can use our model. So what we're talking here in terms of exponential modeling is we're talking about if you have a population. Now you have to stop thinking in terms of math about a population being people. Okay? A population is really anything that you can count. It could be people, but it could be mold spores in a petri dish. It could be leaves on the ground. It could be number of times Lynn's, does an assembly. Or crazy stuff like that. Anything that you can count is a population. And so the exponential model for P changing at a constant percentage rate R over a time frame, in this case is each year. Now, here's the kicker, is that I'll tell you this here in a minute because we already did some crazy stuff. So P of T is equal to P sub 0, where P sub 0 is my initial population. That was 50 leaves in the last column. Times the quantity 1 plus or minus R. Now it's plus if we're increasing. You might see the term appreciate on that one. So if we're appreciating in value, we're going up in value. Minus if we're decreasing or depreciating in value to the t power. Now that power, in here it's referred to in years only because in the directions up here it was referred to in years. In the last problem that we had, it was in hours. Okay? We were talking hours in the last problem. As long as we stay consistent with our time frame, we can use that time frame. If we said something in the last problem like in 35 minutes, how many leaves are on the ground, we would have to convert 35 minutes into hours in order to put it into the formula. Okay? So just so you know on that time frame. Okay? With that being said, let's determine the exponential function with an initial value of 12 and increasing at a rate of 3.5% per year. You find me that right now. 3.5% becomes a decimal of 0.035. Remember that when we're converting a percentage to a decimal, 2 spots to the left to make it be a decimal. If we have a decimal and we want the percentage, then that's 2 spots to the right. Okay? So we got that. So my function, I'm going to say f of t is going to be equal to, my initial value was 12 times, I'm increasing, so that's going to be 1.035 to the t power. Agree? Okay, all right, let's get to the new car. Let's get to that new car smell. So, you purchased a 1979 Ford Pinto. Back in 1985, that was valued at $1,800. This Pinto was pure classic. Okay? And I think the picture should tell you who we're talking about in this story. Okay? All true. So far, everything has been true. Okay? This Pinto was white with red striping, Starsky and Hutch style. For those of you that don't know, Starsky and Hutch was a TV show. He had a Ford Gran Torino, and it was red. Starsky was red, and it had a white pinstripe like this, like on the Pinto here. Oh, hot. Okay? Pure muscle car, all good stuff. Okay? Even had sport rims, your classic Pinto. Okay? It was all the talk of Greenway High School. Okay? Hard to believe, but somehow this hot rod actually lost value at the rate of 7% each year. Side note, every time you buy a car, it loses value every year. Find an exponential function that describes the value of this classic as a function of t in years since 1985. Then go on and find me the value of the Pinto in 1990. Okay? I'm going to give you 4 minutes to get this problem done. All right? So, we first need an exponential type function based upon this classic hot rod. Okay? So, let's go H. I'm going to go H just because it's Mrs. Hill. H of t is equal to what? 1,800. That was our starting value. Times 0.93.
Yep.
Now, because it's losing value, that's the 1 minus my rate. Okay, so 1 minus 7% is 0.93 to the power of t. Okay? Agree with that? Okay, I love it. Now, there's our function, good times on said function. Then it asks us to find the value of the Pinto in 1990. What year are we talking about here in 1990? Year 5. 1990 is a t value of 5 because our function was in years since 1985. So we need to find h of 5. If I find h of 5, I believe that I get $1,252 and 24 cents. Okay. Welcome to the real world. Yep.
Does it start getting back up because it's vintage?
Once it gets vintage, if it's in good condition.
Oh, right.
If it becomes a rust bucket, like my pickup truck, then you just keep it because it's not worth trading in anymore. Okay. Alright. Any questions on that? Tomorrow, what we will be doing is we will be working on the graphing calculators, and we'll be graphing these exponential functions, and then using those graphs to say, okay, when can this function, when does it reach this value, or when will, if we tweak this one little thing, how does that compare to this one and that one, and all that fun stuff. Okay? All right. That's all I got for today. Thanks for playing along.